Hello everybody, and welcome to the beginning of Chapter 6. We are looking at page 27 in the workbook, and in this section we're going to look at an application of integration called finding the average value of a function. To illustrate this problem, let's start with an example. So suppose that the temperature in Rapid City, South Dakota on a winter day is given by the function f of t equals 30 sine of pi over 2t plus 10 degrees Fahrenheit. T is going to measure time in hours after 12 o'clock noon. Okay, and what we're interested in is determining the average temperature in Rapid City between 12 noon and 3 p.m. Okay, so if you look at what we're given to start us off here, we've got a graph of the function. They're asking essentially to find the average value of that function between 0 and 3. That's between noon and 3 p.m. on our time scale. Okay, how might we do that? Well, if you think about what an average is, it's about taking a bunch of numbers and basically adding them up and dividing by the number of numbers that you have to get an average. Okay, so one way that you might visually think about approaching this problem is to just take the temperature at a bunch of different times. Okay, so I'm going to start by just kind of labeling the axis with some times that we're going to take the temperature at. Okay, I'm going to give these times names, T1, T2, T3, and we would keep going until we get all the way to the end of our list. I'm going to call the second to the last one Tn minus 1, and then this one Tn. And imagine at each of those times going up to our function and measuring what the temperature is. Okay, we're going to get a big list of temperatures. Okay, and we can take the average of every temperature that's in that list. Okay, the question is, how would that look if we wrote it down? Okay, I'm going to try to save space here because there's going to be a bit of writing with this. Okay, so the average temperature is just going to be the average of those of the output values of those points. So we would take the temperature at time 1 plus the temperature at time 2 and keep going until we get to the last temperature, and then divide by the number of temperature readings we took, which is n. Okay, now what do you think? Is that going to be the exact value of the average function or average temperature, or just an approximation of it? Okay, if you think about it, it's got to be just an approximation because we just picked out some specific points on this curve. We did not pick out every single time. We just kind of took a sample. But the idea is if we take enough points, we're going to get a good overall idea of what the average temperature is. Okay, now what we're going to do is a little bit of algebra here. Okay, so I'm going to start by recalling a formula, okay, that we talked about when we were talking about numerical integration, and I apologize for kind of writing all over the page, but I'm trying to save some space here. Delta t equals b minus a over n. That was our way of finding the width of a subinterval. In our case, it's going to be the distance between two of these times that we're talking about. And what I'd like to do is to take that formula and to solve it for n. Okay, so first we're going to multiply both sides by n, and get n times delta t is b minus a, and then we're going to solve it for n by dividing both sides by delta t. Okay, why would we be interested in knowing what the value of n is? Well, n just happens to appear in the denominator of our function over here. Okay, so I'm going to go back and substitute in the n. We discovered from above that n is equal to b minus a over delta t. Okay, so if we do that, we can rewrite our whole expression like this. Okay, so now what we've got is kind of a fraction within a fraction. We're taking our numerator and we're dividing it by the fraction b minus a over delta t. In a situation like that, you can multiply by the reciprocal of the fraction that's down in the bottom. That's what we're going to do. Okay, so I'm going to rewrite this as the numerator times the reciprocal of what we have in the denominator, delta t over b minus a. Okay, I'm going to do one more rewriting of that. Okay, the b minus a that you see in the denominator, we can move that to the front of this expression and just rewrite it like this. Okay, and leave the delta t at the end. And this particular part that I'm underlining here, this is underlining. You might remember seeing something like this in Calculus 1. Okay, we can write that sum in shorthand notation as follows. Okay, some of you may have seen sigma notation. Okay, so this is just another way of rewriting the underlined part. Okay, so that thing that you see here is just a shorthand symbol for a sum. It's telling us that we're adding up a bunch of terms that look like this, f of ti times delta t, and the I that you see is a counter. It's just telling us that we're starting at 1 and we're stopping at n, and we generate the exact same sum that we have up here. Okay, let's clear a little of the clutter away here. All right, and now for the key observation. This sum that we're looking at here really represents an approximation of area under a curve. You might remember seeing this in Calculus 1. This is what's known as a Riemann sum, and it's an approximation of an integral, approximate area. Okay, so with that all in mind, let's think back to the problem that we were solving for a minute again. Okay, we started this as a method for estimating the average value of our function. We made the comment that this is not exact because we're just picking n temperature values and adding them up and dividing by n. How would we make this estimate more accurate? Well, we could do it by increasing the number of temperature readings, letting n get bigger and bigger and bigger. And the more temperature readings we take, the more accurate our average should be. So here's our comment. If we let n approach infinity, or let me say it this way, letting n approach infinity, what's going to happen is that we have more and more temperature readings. This delta t that you see up here is going to get smaller and smaller, and in the limit, that sum that we wrote out above here is going to turn into an integral. And so here's what we get. The average value of our function is going to be equal to 1 over b minus a times the integral from a to b of our function. Okay, so what we have just derived is a formula for determining exactly the average temperature, and it involves just taking the integral of our function and multiplying it by the fraction 1 over b minus a. Okay, in the next video, we will do an example. We'll actually redo this example and find the average temperature for this problem.